Hello everyone, in this control engineering estimation and control theory tutorial, we explain how to properly simulate a stochastic or random linear state space model in Python. This problem is very important for simulating state space trajectories of dynamical systems that are under the influence of process disturbance and measurement noise. Also, this problem is very important for developing and simulating the behavior of stochastic state estimators such as Kalman filters, particle filters, etc. By the end of this video tutorial, you will be able to simulate a stochastic state space trajectory of a state space model shown over here. The state space trajectory is shown over here. This is the starting point and this is the end point. And you can clearly observe the randomness of the state space trajectory. This randomness mainly comes from this vector over here. This vector is the process disturbance and this vector is completely random. The time evolution of the first state of the state space model is given over here. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start with explanations. We consider a linear stochastic state space model given over here. Xk is the state vector at a discrete time step k. Uk-1 is the control input vector at the time step k-1. Wk-1 is the process disturbance vector that is also known as the process noise vector at the time step k-1. Yk is the observed output vector at the time step k. Vk is the measurement noise vector at the discrete time step k. A, B, and C are the system matrices. Here we assume that the random vectors Wk and Vk are distributed according to some predefined distributions. In this tutorial, for simplicity, we assume that both of these vectors are normally distributed with given mean vectors and covariance matrices. However, everything explained in this video tutorial can be generalized to random vectors with arbitrary distributions. Let the mean vector and the covariance matrix of Wk be denoted by mu, W, and Qw. Similarly, let the mean vector and the covariance matrix of Vk be denoted by μv and Qv respectively. By using the mathematical notation, we can write these vectors and their distributions like this. Over here, this math calligraphic n is the mathematical notation for the normal distribution. The first entry in this notation is the mean vector and the second entry is the covariance matrix. This symbol over here, that is the symbol that looks like a similarity sign, means that the vector on the left side of this symbol is distributed according to the distribution on the right side of this symbol. Our goal is to simulate this state space model starting from some initial state x0. That is, our goal is to generate a state trajectory represented by this series and the output trajectory represented by this series. To explain how to simulate a state space model in Python, we need to use a test case. As a test case, we use a second-order mass spring damper system originally introduced in our previous tutorial. A link to our previous tutorial explaining the mass spring damper system will be given in the description below this video tutorial. Here is the mass spring system. And here's the procedure for deriving the state space model. We use the second Newton's law, and finally, after several derivations, we obtain this state space model. Here again is the summarized state space model. A matrix is given over here, B matrix is given over here, and C matrix is given over here. In this state space description, Ks is the spring constant, Kd is the damping constant, and m is the mass. The C matrix and its structure tells us that we only measure the position of the mass. The first state of the mass spring damper system is the position, and the second state is the velocity. The first step is to discretize the state space model. To discretize the state space model, we use the backward Euler method. The backward Euler method approximates the state derivative by using the backward finite differences. That is, we approximate the first derivative of state like this: xk minus xk minus 1 divided by h. Over here, h is a sufficiently small discretization time step, and xk is actually notation for continuous state x at the time instant k times h. By substituting this approximation in our continuous time state space model, we obtain this equation. Then, by multiplying this equation by h, we obtain this equation, and after several transformations, we finally obtain this equation. Next, by replacing the approximation symbol with the equality symbol, and by replacing uk with uk minus 1, we obtain the discretized state equation having this form. Over here, AD is given over here, and BD is given over here. The replacement of UK by its delayed version UK minus 1 does not change anything qualitatively about our state space model. The output equation stays the same. Before we explain the Python script for simulating the state space model, we need to explain why we use the backward Euler method. Namely, we can also approximate the first derivative of the state space vector by using the forward difference discretization. That is, we can use this equation. And then we can follow the same procedure, namely, we can substitute this equation in our state space model to obtain this state space description, and finally to obtain this discretized version of our state space model. However, the resulting discrete time state space model given by this equation might not be stable. On the other hand, the discretized state space model obtained by using the backward Euler discretization method has much better stability properties than this state space model obtained by using the forward Euler method. And that's the main reason why we are using the backward Euler method. To summarize, we use the backward Euler method to ensure the stability of the discretized state space model. Also here we have to emphasize that we discretize the continuous time model that is not affected by the measurement and the process noise. Later on, we will add the process and measurement noise to the discretized state space model. On the other hand, if we would start from the continuous time model that is affected by the continuous time measurement and process noise, the discretization procedure would be much more complex. More about this in our next video tutorials. Next, we explain how to simulate the stochastic state space model in Python. The first step is to import the necessary libraries. First of all, we need the NumPy library, then we need the plotting function, and finally, from SciPy.stats, we need to import multivariate normal. The SciPy library has a module called stats, and this module contains a number of useful functions for simulating stochastic processes. In this tutorial, we use this function multivariate normal to create and to draw samples from multivariate normal distributions. Next, we need to define the mean and the covariance of our process disturbance. Over here, we define the mean vector, and over here we define the covariance matrix. We do the same thing for the measurement noise. Here's the mean of the measurement noise, and here's the covariance matrix of the measurement noise. Since the measurement noise is scalar, this is basically a variance of the measurement noise, and this is a simple scalar mean of the measurement noise. To create the distributions, we use the function multivariate normal. The first keyword argument is the mean, and the second input argument is the covariance. We do that for the process disturbance and for the measurement noise. Next, let's learn how to draw samples from these distributions. For example, over here, I will draw a sample from my process disturbance distribution. I specified the name of the object, P distribution, and then I called the function RVS, and I specified the size of the sample. After that, I'm simply reshaping the result such that it fits in the format that I need. Okay, so let's see what will happen over here. First, let's execute this part, and let's see what happens over here. Okay, great. So here's a sample of my process disturbance. It's a vector of 2 rows and a single column. Now, if I repeat this command, or this function, or better to say the call of this function, I will obtain another random vector. This is very important. We do the same thing for our noise. We just need to write the name of our object, RVS, then we specify the size, and over here we don't even need to reshape it. And here it is. Here is a sample of my measurement noise. Here is another sample, yet another sample, etc. Next, let's erase these two code lines since we don't need them. Okay, the next step is to define a continuous time state space model and to discretize it. Let's do it. First of all, we need to select the parameters of our continuous time system. Here's the mass, here's the spring constant, and here's the damping constant. Then, over here, I define the continuous time state space matrices. This is my A matrix, this is my C matrix, and this is my B matrix. Next, I define the discretization constant, h is equal to 0.005, and over here I discretize the continuous time state space model to obtain the discrete time system matrices A, B, and C. Next, I define the number of simulation steps. In my case, I will simulate the state space model for 1500 discrete time steps. Next, I select the initial state, and over here I select the control input, or better to say a time series of control inputs where every entry of this time series will actually be a control input applied at the corresponding time step. In my case, I will simulate the response of the system to a simple step control input. In my case, the applied input is 100 newtons at every time step. Next, I need to define arrays for storing the state and output trajectories. Here is how I define the state array and output array. And finally, I initialize my state array with initial condition. Next, let's simulate our state space model. We need to simulate this recursive state and output equations. Here's how we do it in Python. We define a for loop where the index I goes from 0 to sim steps minus 1. First of all, we simulate this equation. Here's how we do it in Python. xk over here is this part over here. xk minus 1 is this entry over here. And this expression numpy.mat multiplied a, and this term is actually this multiplication. Similarly, this part corresponds to b times uk minus 1. And over here, wk minus 1 is simulated like this. We simply draw a sample from our process disturbance distribution. The output equation is implemented in the same manner. Yk over here corresponds to this part over here. This multiplication is actually c times xk, and over here we draw a sample of our process, or actually of our output measurement noise. Simple as that. So what's happening over here? We perform vector matrix multiplications, A times xk minus 1, b times uk minus 1, and over here we draw a sample of our process noise. We do the same thing for our output equation. Here we multiply c and xk, and over here we draw a sample of our measurement noise, and that's it. And finally, let's plot the simulation results. First of all, we need to create a time vector for plotting the results. Here's how we create the time vector. Over here, we plot the time response of our system. We define a figure, then we plot the time vector on the x-axis, and on the y-axis we plot our state. We set the color and the line width. We set the title, x label, y label. We adjust the parameters of our plot, that is, we adjust the font size, we set the grid, we save the figure, and we finally show the figure. So let's see the time response of our state. I will execute the code from here until here. And here it is. Here's our first state and its response with respect to time. Okay, so to see the second state, we will simply change this index over here and set it to 1, and let's see the output. Here it is. This is the velocity, and over here is the position. Next, let's learn how to plot the complete state space trajectory. To plot the state space trajectory, again we need to define a figure, and over here we need to plot. On the x-axis we plot the state x1, and on the y-axis we plot the state x2. We set the color, specify the line width, and specify the transparency. Next we set the title of our plot, x label, y labels, we set the font size, we set the grid, and over here we specify, or better to say, we mark the starting point of our state trajectory with a red circle. The marker is O, and the label will be start. Similarly, to better visualize the state space trajectory, we mark the endpoint with the black circle. Finally, we introduce the legend, we save the figure, and we show the plot. So let's look into our simulated state space trajectory. Here it is. Looks very nice. Here's the starting point, and here's the end point. And we can clearly observe the stochastic nature of our state space trajectory. This stochastic nature is mainly due to the fact that the process disturbance is randomly affecting our dynamics. We can observe what will happen with this state trajectory if we change the covariance of our process disturbance. Over here, I will increase tremendously the covariance matrix of our process disturbance, and let's see what happens now. And you can see a very stochastic state space trajectory. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.